Hello and welcome to this film, which is the first of 6 films from the higher level energetics topic. You might be looking at the title and thinking, why am I doing Hess's law calculations again? And that's because in the higher level energetics topic, not only do you have to be able to construct the cycles from equations that you've been given, but you also have to be able to use definitions of terms to actually think what equations you're going to use in these things. Okay, so hopefully by the end of this film, you'll at least know and possibly remember the definitions of 2 important terms, the standard enthalpy of formation and the standard enthalpy of combustion, and you'll practice writing some equations to show these processes taking place. Now, if we're talking about standard enthalpy changes, it's important to know what we mean by standard, and there are various meanings of standard conditions. If we're talking about standard laboratory conditions, so that's materials in their standard states, we're talking about a temperature of 25 degrees centigrade or 298 Kelvin and a pressure of 1 atmosphere or 101.3 kilopascals. This is different to standard temperature and pressure, which is confusing, but it's worth bearing in mind. You'll normally be talking about standard states in this topic, but if you're referred to standard temperature and pressure or STP, then you're talking about 0 degrees centigrade or 273 Kelvin and 100 kilopascals. So as I say, mainly it's going to be done under standard states in this topic, but just be on the lookout. Right, so our first definition here, the standard enthalpy of formation. Let's just have a look at the symbols first. Okay, delta H for change in enthalpy. Formation is represented by this little letter subscript F, and then we've got superscript theta, or as I learned it in a British school in London, the underground sign. Okay, so delta HF underground sign, or the standard enthalpy of formation. This is the enthalpy change when, and a lot of these definitions as we've seen before start with this, the enthalpy change when 1 mole of a substance is formed from its elements and everything is in its standard state. Now, we'll have a look in a moment at how you might write an equation for this, but if you just think about this for a moment, if we're talking about 1 mole of any substance being formed from its elements in their standard states, if we talked about an element in its standard states being formed from its elements in their standard states, then we wouldn't expect an enthalpy change for that because it's one thing turning into the same thing. So it's 0 for all elements by definition. Okay, let's just have a look now at what it might look like for a non-elemental substance. So here's the standard enthalpy of formation of butane. Okay, butane happens to be a gas under standard laboratory conditions, so its standard state is gaseous. And what this says here is that the standard enthalpy of formation of butane is minus 127 kilojoules per mole. Now, if you're going to use that kind of data properly in a higher level question, you're going to need to be able to picture what that actually refers to. In other words, you've got to have in mind a reaction equation. So if we know the definition, then we know that this involves 1 mole of this substance being formed. Okay, that's going to be a gas. And it's important we include state symbols because then we're showing we know what states these things are in standard laboratory conditions or in their standard states. The enthalpy change for this process is minus 127 kilojoules per mole when this material is made from its elements, carbon and hydrogen. But carbon is written as a monatomic substance. Hydrogen does not exist as a monatomic substance under standard laboratory conditions. It's diatomic. So we have to have the elements with their correct formulas on the left-hand side, and we have to have the right number of them to make sure that the equation balances. And they have to be in their standard states. So carbon would be a solid and hydrogen a gas. Okay, so in other words, I'm able to write an equation for this piece of data because I know the definition of the standard enthalpy of formation. Okay, and if I don't know that definition, writing equations becomes very difficult and doing Hess's law calculations becomes even harder. Okay, here's our next definition, and again looking at the symbols first, you can see that all that has changed is that the F has turned into a C, so we've now got delta HC underground sign, or delta HC theta, standing for the standard enthalpy change of combustion now. So this is the enthalpy change when, again, it's this same thing at the start of the definition, when 1 mole of a substance is burned completely in oxygen, with all substances in their standard states. So let's have a look and see if we could look at some data involving a standard enthalpy of combustion and turn that into an equation. Because unless we can do this, we don't really know what this is talking about, okay? So we're now talking about 1 mole of butane burning in oxygen. Oxygen in its standard state is O2 and it's a gas. Butane is also a gas, and what we're going to form if we have plenty of oxygen and we burn it completely is carbon dioxide, which under standard laboratory conditions is a gas, and water, which under standard laboratory conditions is a liquid, even though when you burned this in oxygen you wouldn't immediately form droplets of water, you'd form water vapor, but the enthalpy change is measured once that vapor has condensed back to water. Okay? Now we've got 1 mole of this substance burning, so we know what quantities we're going to put in our equation. We've got 4 carbons, so 4 CO2, 10 hydrogens, so 5 H2O. We've now got 13 oxygen atoms here, so 6.5 O2 over here. Okay, and again we've managed to write an equation with state symbols, knowing what the standard states are for this particular piece of information. Now, it can sometimes be the case that the standard enthalpy of combustion is actually the same as the standard enthalpy of formation of something, or at least the numbers can seem the same. So if we have a look now, just I suppose there's a bit of practice of writing these equations, the standard enthalpy of formation of water is equal to minus 286 kilojoules per mole. 1 mole of water, remember, in its standard state, liquid, forming from its elements H2 and O2 in their standard states, so both gases, right? And 1 mole of this, so I've got to have half a mole of oxygen. If I wrote an equation for the standard enthalpy of combustion of hydrogen, well, it would look very similar to this. We'd have 1 mole of hydrogen being burned in oxygen to form water, and everything would be in its standard states. So it's no surprise to see here that the enthalpy change for these two pieces of data is exactly the same. Anyway, hopefully you've seen how we can turn information about an enthalpy of formation or combustion into a reaction equation, but also how important it is to know the definitions of these terms, because otherwise you've got no chance of writing a correct equation. And if you can't write the correct equations, you won't be able to put them into cycles properly. So make sure you remember these definitions, make sure you know how to write the equations, and make sure that if you've got any questions or comments, you come and see me as soon as you can, or post a comment on YouTube.